Hello and welcome back to Data Science CastNet. It's been a while. We're back with a new video and actually potentially a new video series in which I'm going to run through some foundational concepts around language models, these large language models, through the lens of this Kaggle LLM science exam competition. So in this video, we're going to start by looking at how we can use existing language models to solve these kinds of tasks just off the shelf in a so-called zero-shot setting. And then in future videos, we'll look at ways that you can fine-tune the models for something like this, where it's a task-specific model that you're creating, and also look at ways to create more data and evaluate these models and so on. That's all in the future though. In this video, we're just going to get started with this competition without actually training any models, seeing what we can do off the shelf. So the goal of this competition is to answer these kind of multiple choice questions, these science-related multiple choice questions, and the questions themselves have been generated by giving GPT-3 snippets of text from Wikipedia on scientific topics and asking it to come up with these questions. And so they're asking us to look at a question that has 5 possible answers and to submit our predictions where we guess, what we think the best guess is, then the second best and the third best guess. And the way it's scored is that you get 1 point if your first guess is correct, you get a half a point if the second one is correct, and you get a third of a point if the third one is correct. So this is this mean average precision. It's kind of like rewarding you for getting the correct answer on the first time, but allowing you 3 different guesses in case there's maybe some ambiguity or something. So to start with, just to get a feel for whether we can even expect a language model to be able to do this kind of task, one thing we can do is just try out something like ChatGPT, right? A hosted model, and we can copy in one of these questions and ask it to answer in this format where it gives 3 guesses. So I've just copied and pasted one of the questions from the dataset here, and ChatGPT has come back. It hasn't followed my instruction to only guess the letters. I could have maybe rephrased this to get that behavior, but it has come back with 3 guesses. It says its best guess is E, second best guess is D, and its third best guess is A. And I didn't actually pick this question arbitrarily because I wanted to show that some of these questions can be very ambiguous. In fact, in this particular one, what is the Roche limit? If you go look up the Wikipedia article on this topic and read through it, you'll see that both D and E seem very correct. It's the distance at which the tidal effects would cause an object to disintegrate. The Roche limit is the distance at which tidal effects would cause an object to break apart. They're very similar. In fact, I have a hard time saying that both aren't correct. I think maybe D is more concise and maybe thus the better one, and that's what's marked as the correct answer. But just to flag, these are hard questions. Sometimes there's ambiguous questions. So we can't expect ever to get 100% because I doubt that the questions have 100% perfectly unambiguous answers, but we want to get close. So as maybe a useful benchmark, let's see if we can go from typing in ChatGPT in the web interface here. What if we can use this model just to establish a baseline? We can't submit this on Kaggle because this is a code-only competition. So the way this works is you submit a notebook that runs without internet access and must make its predictions on an unseen test set. But what they have given us is some training data with 200 example questions that include the answer, and we can use this to benchmark our approaches today. Since we're not using them to train anything, we're just evaluating. So I have this notebook here, and what I've done is I've added my OpenAI API key as a secret on this notebook. So I can load that in, and then I can use that to query the OpenAI API and use GPT 3.5 through their API endpoint as opposed to the chat interface. So we can load up our questions. If we pick a random question, the general idea here is that we're going to prompt the model in such a way that when it completes, when it auto-completes its return message, we hopefully get what we want. And so this is my first pass. I'm not an expert prompt engineer, but I've said answer the following multiple choice question, providing your 3 top guesses in the order from most to least likely using the following format. This is in the system message, which is a lot nicer for enforcing a particular format than just asking it as a user, but still not perfect. And then in the user message, I'm including the actual question as well as each of the answers. And we'll print this out. And then just to try and enforce again, to really encourage the model to follow the format that we want, I've added this little reminder on the end of the prompt. Remember to answer only with the letters corresponding to your answer. So if we call the API, I've got the chat_completion.create function call here with the OpenAI library. We pass in our system message and our user message, and we expect an assistant message back. And sure enough, that's what we get. And in this case, it does exactly what we asked. It only responds with 3 letters, A, D, E. for its three guesses as to the answers of this first question about MOND. So if we want to see how well this does, we can run it over all of the training data, or in this case I'm just doing half because I wanted to save time. The same approach, I've just copied and pasted into this for loop, one for each row in the training data set. And when we come back, we can see that we get a score of 0.74. So remember, you get 1 point for a correct in the first position, half a point for the second guess, a third of a point if the third guess is correct. So I'm running through and keeping track of the score. And in this case, we get 0.74, which is not bad. If you look at some of the discussions, you'll see other people have found, for example, this person found GPT 3.5 Turbo got 0.78. They had a slightly different format for the prompt. You'll see some other people who have tried some different things and getting around that same score. So that's a nice baseline, right? This is, okay, we take a good model. GPT 3.5 is a really good model. We just do this like some form of evaluating it, and we get our scores. Now GPT-4 does even better. This person just manually copied and pasted into the GPT-4 chat window, and they were able to calculate a score here, and it was 0.87 accuracy at 1. In other words, it got the first guess correct 87% of the time. If you then did the normal scoring with this mean average precision at 3, it would score even higher. So that gives us a really nice upper bound to say the best publicly available model. When I manually prompt it, it gets 87% correct first try, and would like to get even more correct if you allowed it to guess again and again for the second and third tries. Okay, so before we move on from this baseline, I did want to show one trick which is going to come in useful in later videos when we talk about data generation as well, which is that here we're basically begging the model to follow this format. We're saying, please, please, please answer in this format, A, C, D, for your 3 guesses. And that's not ideal. What we'd really want is some way to constrain the response or to get some kind of structured output here, because our answer format always looks the same for this problem. And so there is one way to do that with the OpenAI API, and that is to use this function calling API. And what this is it lets you, well, it's designed to let you run external functions, right? Like a calculator app or a weather application to let GPT rather run these functions as part of a conversation. But the way that it works is that you just specify what your function parameters look like using this very formal sort of JSON schema. And so here I'm saying, well, pretend there's a function called answer question that's going to answer whatever question has been provided. I can then define what the inputs to that function look like. I can say I would like a reasoning input that's a string, and I can describe what that is expected to look like. And then I can say I want an answers input that's an array, and each of the things in the array should be a string, and it should be one of these options. And again, I can give a description, right? So this is now, we're telling the model, by the way, I have a function that presents your answer to the user. And now when I ask for my chat completion, I again pass in the similar system message and user message, but now I'm also saying, by the way, you can use any of these functions, which in this case just has the one, and this function call parameter says, I would like to enforce that you must use this function. So I'm saying you must use this answer question function. And using this is pretty nice, because now instead of getting back this freeform like text answer, we get back a dictionary. And the dictionary has the parameters that we've asked for. It has the reasoning parameter with the explanation, and then it has an answers parameter with the answers in an array. So no more passing the string. If the model used to give an answer like this, right, with a lot of extra waffle and explanation, well, now we don't have to worry about that, because we're saying only give me the parameters that I asked for this function. And if I use that, in this case, I get about the same score. But the difference is I don't have to be relying on the model to follow a specific format. Instead, I'm getting my answers nice pre-processed in this structured JSON object. So that's much nicer, a nice little trick for you there. But anyway, a little bit of a diversion. Still, we're learning, and that's the whole point of this. Okay, so we can't submit this because this requires internet access, right? It's sending these calls to OpenAI over the internet and getting the responses back. We don't have access to the model weights of GPT-3 that we can somehow zip up and upload to Kaggle. So how do we fix that? Well, the example that I'm going to show here is going to instead rely on an open source model. So this is a model called Llama 2. So we're installing some libraries, loading in the data that's provided on Kaggle. You can just download the CSV and upload it here. And in this case, I'm downloading the base Llama 2 7 billion parameter model from Hugging Face. And it is open source, but you do need to request permission to access, which is why I also have to log into Hugging Face here in the notebook. And so we download this 7 billion parameter model. So this is an open source attempt to replicate something like these large language models like GPT-2, 3, 4, etc. But this hasn't been tuned to be an assistant. This is the base model. So this just predicts the next word in a sequence. And we're going to say, okay, given this capability, I don't have any fancy chat syntax. I don't have a function calling API. Can I achieve that same sort of thing where I would like to get this constrained answer of A, B, C, D, or E out of this model somehow, or find another way to answer this question in a very like strict technical classification sense, as opposed to just produce some more text. And so we're going to explore that in this notebook. The first idea that is worth trying is to leverage the fact that this is a language model that predicts the most likely next token. And so if I can come up with a template where I have maybe an instruction, a question, the series of answers, and then the text answer : hopefully, if the model does a good job, the most likely next token is going to be the letter corresponding to the correct answer, right? And so if I feed in this whole string to the model and I say, now predict the probabilities of what the next token could be, that's exactly what it's been trained to do. Hopefully, the probability for the correct answer will be higher than the probability for the wrong answer. And so we can try this out. We feed in the first question, what is the Einstein at Home project? We get our 5 answers, then we do the answer : and we look at the probabilities for the letters A, B, C, D, and E. And I'm looking at the, this is the model outputs. It has a .logits attribute that contains these one output for every possible token, for every possible location. So we want the last location, like what is the next token after the string that I've just fed in? And we can see we have a probability of 0.23 attached to the token for A, and only 0.15 for the token for B, 0.1 for the token for C. And so you can see that here the model is saying the letter A is the most likely next completion in this sequence that includes the question and the answers, and then B, and then D, and then E, and then C. So that's its ranking based just on the probabilities of the next token. And so the predicted answer here is A. The actual answer is C. So this falls flat on its face in this particular example, but we can try it for all of the questions and we can see how well it does. So I've just taken that same idea. We're running through all of the rows in this trained data frame. We're turning each one into this prompt. We're looking at the logits, the predictions from the model. We can turn those into probabilities if we like, using softmax. And then we're ranking these. So I would like to rank them from the most to least likely, and taking the top 3, we can score. And so I've printed out some examples here. We get our first 3 questions. In this case, it thinks D, B, and E. Actual answer is A, so that's wrong. In this case, D, C, and B, with, let's see, D being the most likely out of the 5. And that is actually is that the right answer? No, that's wrong too. Bad example. But here, the actual answer is D, and that's the second most likely. So if we look at our accuracy at 1, it's only 30% accurate, right? Which, if you were just guessing, you'd be 20% accurate. So this is pretty bad. The mean average precision at 3 is closer to half, like 0.5. So if you look at the leaderboard, you'll notice that some entries were lower than that, but a lot of them are much higher. In fact, let's have a quick look at the leaderboard just to get an idea of what other entries are. So the top few teams are in the 0.8 range. Straight away, it drops down to 0.7 something, and that's where most of the entries are, until we get to, let's see, where are we? Spoiler alert, we're going to try and get up closer to 0.7. But yeah, you really have to go a lot further down to get to 0.5. So we're not doing too well just yet. And part of this is because we're just using a base model, and it's only trying to predict the next token. We haven't done any prompt engineering. Like maybe you could say, you know, as an expert scientist, it's obvious that the answer is : and then the token. But even that, what that's doing is just relying on the model to be able to look back at these 5 options, choose which one is right, assign a higher probability to that letter. That's not ideal. And so there's ways we could try and get around this. Maybe we could have the model produce a freeform answer to the question first, and then compare that with the answers somehow. we could use a chat model that was more like amenable to following instructions. But the approach that I want to highlight, the final trick from this video, is to instead look at something called the perplexity. And so at the moment, we're feeding one set of text, we're encoding it, and we're feeding it through the model all at once, and we're looking at the probabilities for just the next word, right? And that's giving us some signal, but it's not a very strong signal. It doesn't do very well. So instead, we can take this approach where what we do is when we feed a string through the model, we get a probability for the next word. For every word, there's a probability for the next word, right? So if I take a string, this is a very likely string. Then if I look at the probability for the next word after this, is probably quite high. After is, almost certainly A is quite likely, right? So we can do, not just for the final word, for some hypothetical answer, but for every word, we can measure how likely is the next word. So here, running through that string, combining these logits, these are the outputs, one output for every token for every word in the sequence, we can run through and we can see, okay, if I starting the sequence, this is not that likely, but once you've said this, the word is 15% probability of following on after that. And after is, the word is actually really likely to follow that, and so on. And so this gives us a measure one per each token, and we can take some sort of combination of these. There's technical ways of calculating the actual perplexity score itself, but the idea is that some measure of how likely on average is the next word given the current word. And the idea here is that if I have a nice reasonable sentence, like this is a very likely string, it'll have some perplexity. If I have a completely garbled or meaningless string, it'll be worse, right? It'll have a higher perplexity. Each token is relatively unlikely. Now, the reason we're interested in this is that instead of saying, here's the question, here's all 5 possible answers, now produce a letter as to which answer you think is right, we can instead just match up one answer with the question at a time. Because if the question is followed by the answer directly, then the correct answer is more likely to follow on from that question, whereas an incorrect answer is going to come up as relatively unlikely to follow that question. So what we're going to do, we've given a set of 5 possible guesses. For each one, I'm going to do the question and then that particular answer, right? So running through A, B, C, D, and E, and I'm going to calculate the perplexity. So for this question here, just a random sample, we had a perplexity of 1.8 for A, 1.7 for B and C, 1.66 for D, and 1.7 for E. And here, lower perplexity means the model was expecting that continuation more. And so the correct answer is D. We got this right. The predicted answer, i.e. the lowest perplexity answer, was in the position for D. And so this is like a step above just looking at the predicted next token. This is instead taking a whole sequence and saying, as a whole, how likely is this sequence of question and answer? Still not perfect for reasons we'll explain, but if we try this, we can do this for all the rows in our training set. Our accuracy for the first guess goes up from 30% to 50%, and our score goes up to 0.635. Now, this is not an approach I came up with. Other people on the leaderboard have tried this, so I would say go and check out the notebooks, don't use mine. I'll share the code just for reference. But if you go and check on the discussions, you'll find things like this notebook, which is the original one that introduced the idea, and then this one here, this ranking, where they tried many different models with this approach, right? So we have, in this case, let's see, they're trying Red Pajama, Dolly, Stable Language Model, MPT, and Falcon. And if we go read through the code, they've got a perplexity calculation, they've got their metrics, and so they're going to go and create this candidate where you have the question, and then the answer, and then one particular answer, and they're going to do that for each of the 5 candidate answers. And then calculate the perplexities, find which are the smallest perplexities, and use those as their predictions. And when they do this, let's see, on the training set, they score 0.65, 0.66, so in that same sort of range. And they ensemble them together. I think they score on the leaderboard something like 0.66. So this is an improvement over the we're getting 0.63, but there's lots of iteration. You could change this prompt. The format is pretty arbitrary, so there's some prompt engineering there. But yeah, that's this perplexity approach. And the neat thing is there's no training. You're still not fine-tuning the actual model. You're just using it as an off-the-shelf language model, right? A base language model, just predicting the next token. But we're using those predicted probabilities in a way that we can now turn this into a classifier. We're not showing it any examples of correct questions. We're not doing any like in-context learning. We're not doing giant prompts full of potential like hints and context. We're just saying, do your job as a language model, predict us the probabilities for each next token. But by interpreting those, we can turn this into a classifier. So I thought that was pretty fun. Like I said, I'll share links to the different discussions and the notebooks down below. With these open source models, it's pretty impressive what they can do, but you can see they do lag behind the much larger GPT-3 and GPT-4 models. Still, I think it's a really interesting exercise to see how much you can get out of this. So yeah, please do give it a try. Let me know if you boost the scores at all. Otherwise, thank you so much for watching. And in the next one, we'll start looking at ways that we can go beyond just the zero-shot approach. So I'll see you then.